Hi everyone, it's Mr. Baker here, and today we're going to be looking at the principle of moments. So we're going to be looking at the principle of moments, and this is the question we're going to ask. We're going to ask, how do I know if something is balanced, or how do I know if something is in equilibrium? Right, so let's do a bit of a recap. Can you remember moments? We did it a few lessons ago. So a moment is a turning force, and a moment equals the force times the distance, or really the force times the perpendicular distance from the pivot. So if I've got a pivot or a fulcrum here, and I've got a force that is creating a turning force around that pivot, so it's forcing down on this plank that is resting on this pivot, then if I'm pushing it down, then it will create a turning force, and I can work out what that turning force is by multiplying the force times this perpendicular distance here, not the distance from the force directly to the pivot, it's the perpendicular distance, the force times this distance here. So we're going to be looking at the principle of moments today. So it's all to do with moments. Basically what it says is the total anti-clockwise moments equals the total clockwise moments. So the moments that are trying to push this plank around this pivot this way are going to equal the total of the clockwise moments if that object is balanced. So if this object is in equilibrium, or if it's balanced, then these two moments will equal each other. And it says total because if I've got more than one force pushing down here, so I've got more than one moment on the right hand side, I would add up all the moments on this side, and then if they equal all of the moments on this side, then I would know that yes, that object is balanced because of the principle of moments. And the object will be balanced when the total anti-clockwise moments equals the total clockwise moment. Okay, so I'm going to show you this moments lab from the PhET website, another brilliant simulation from the PhET website. Here we've got like a seesaw, and we've got a pivot or a fulcrum here, and we've got a length here. Now the centre of mass is right here, and so the moments on that are turning it clockwise equal the moments that are turning it anti-clockwise, and so this seesaw is in equilibrium, it is balanced. But if I put a brick, can I move a brick? So when I put a brick onto this side, you can see it becomes unbalanced. So to balance that up again, if I've got a moment here that is going to be equal to the force on here, if we say the gravity is 10, then I've got a force of 50 newtons times by 6. So 50 times 6, I've got a moment of 300 newton meters that is acting clockwise. I'd have to make a moment of 300 newton meters anti-clockwise. So I could do that most easily by just putting 5 kilograms, so 50 newtons at the 6 meter mark there, and that would be exactly the same. Okay, so that's what I could do. That's one of the things I could do. Let's put another mass on here. So now I've got a moment to the right, and now I've got the sum of the moments. So the sum of the moments on the right hand side are going to be equal to 6 times 50, which is 300, times 4 times 50, which is 200, so that I've got a moment of 500 newton meters. So if I can make 500 newton meters go anti-clockwise, then I will be able to balance it. So here I've got 500 newton meters acting around anti-clockwise, and I've got 500 newton meters acting clockwise, and so this is in equilibrium because of the principle of moments. The principle of moments says that the sum of the moments acting around in the clockwise direction equal the sum of the moments acting in an anti-clockwise direction, and we've just shown it there. Okay, so let me show you a couple of examples. So the first example here then, so is this system balanced? Is it in equilibrium? And then you need to explain how you know if it is or not using maths to describe it. So here I've got 8 newtons creating a moment at 50 centimeters around this pivot clockwise, and I've got a 10 newton force creating a anti-clockwise moment at a distance of 40 centimeters from this pivot. So if it is balanced, then the clockwise moments will equal the anti-clockwise moments. So what I need to do is I need to calculate the moments, and then we need to see if they're the same. If they're the same, then it's balanced. If they're not, then I know that it must be turning in one direction or the other. So the force times the distance on the left is going to be my anti-clockwise moments, and that's got to equal the force times the distance on the right if this is imbalanced. So the force is 10 times the distance of 40. Now I'm doing this in Newton centimeters, and that's fine, as long as I keep consistent with the units. So 10 times 40 is 400 Newton centimeters anti-clockwise, and on the right I've got 8 times 50, which is 400 Newton centimeters, and so since the anti-clockwise moments equals the clockwise moments, the object is balanced. Another example then. So this time we're taking moments about the pivot to find the distance x. So we've got some moments that are pulling around clockwise around the pivot, and we've got a moment that is pulling anti-clockwise. So we'd need to work out so the system is obeying the principle of moments, so we know that it's balanced. So if we know that it's balanced, then we can just work out the clockwise moments, work out the anti-clockwise moments, and then from that information we can find out what x is. So since it's balanced, we know the total anti-clockwise moments equals the total clockwise moments. The anti-clockwise moments equals 20 times x, so we've got the force 20 newtons times the distance x, that's the one that's pulling anti-clockwise around the pivot. The clockwise moments equals 10 times 50, so we've got a force of 10 newtons at 50 centimeters pulling in a clockwise direction. We've got to work out the sum of the clockwise moments, so then we've got to do 12 times 90 and add that on. So we've got a 12 Newton force at the end, which is at 90 centimeters. So those two moments are 500 plus 1080. So the clockwise moments equals 1580 Newton centimeters. So we know that 20 times x, which is the anti-clockwise moments, equals 1580, which is the clockwise moments. And we can rearrange that to find that x equals 1580 divided by 20. So x equals 79 centimeters. Okay, hopefully you can follow that through. So these are the things that you should be able to do then at the end of this lesson. You should be able to calculate the moment, or the turning force of an object. You should be able to define the principle of moments. You should be able to use calculations of moments to determine if an object is balanced. And you should, if you know that an object is balanced, use that information with the principle of moments to find out an unknown distance or an unknown force. Okay, so how do I know if something is balanced or in equilibrium? Well, from the principle of moments, if something is balanced or in equilibrium, then the clockwise moments, the sum of all the clockwise moments equals the sum of all the anti-clockwise moments. Okay, right, that's the end of this one on the principle of moments. I've been Mr. Baker, and I will see you next time. Thank you.